Everything you have been told about the beginning of the universe is probably wrong. Not slightly wrong, not technically misleading, but wrong in a much deeper and more important way. You have heard the story countless times. In textbooks, in documentaries, in popular science videos. A story told so often that it feels unquestionable. The universe began in a single moment. A moment called the Big Bang. A beginning of everything. The birth of space. The birth of time. The origin of all matter and energy. It sounds definitive. It sounds settled. It sounds like one of those rare scientific questions we have already answered, but we have not. What the Big Bang actually describes, and what it does not, is one of the most misunderstood ideas in all of modern physics. And the misunderstanding is not a small one, because the Big Bang, as a scientific theory, does not say that the universe began. It does not say there was a first moment of time. It does not tell us how everything came into existence. In fact, when physicists speak carefully, they will tell you something far less dramatic and far more unsettling. They will tell you that the Big Bang describes the universe after it was already here. That it explains how the universe evolved from a hot, dense state, but not how that state came to be, and not whether there was a beginning at all. The idea of a cosmic beginning is something we have added ourselves, a story we tell because our intuitions demand one. We are creatures who experience time as a sequence, before and after, cause and effect, birth and death. So when we ask about the universe, we instinctively ask the same kind of question we would ask about anything else. When did it begin? But physics does not owe us intuitive answers. And the universe is not required to fit the stories our minds find comfortable. The uncomfortable truth is this: the word beginning may not apply to the universe in the way we think it does. To see why, we have to be very precise about what the Big Bang actually is. Because the Big Bang is real. The evidence for it is overwhelming. Galaxies are moving away from one another. Space itself is expanding. The cosmic microwave background fills the universe with a faint afterglow of an earlier, hotter state. These observations are not speculative. They are measured, repeated, confirmed. But none of them tell us that the universe came from nothing. None of them tell us there was a first moment. None of them tell us that time itself had a starting point. Those conclusions come from pushing the theory beyond where it can speak reliably. When physicists run the equations of cosmology backward, they find something strange. As they go earlier and earlier, the universe becomes hotter and denser. Eventually, the mathematics predicts infinite density, infinite temperature, the point where the equations stop making sense. This point is often described as the beginning, but that description is deeply misleading, because an equation producing infinity is not nature telling us what happened. It is mathematics telling us that the theory has reached its limit. The Big Bang is not a moment in time where the universe suddenly appeared. It is a boundary of our current understanding. And boundaries are not the same thing as beginnings. This distinction matters more than it might seem. Because if the universe did not begin in the way we imagine, then many of our most basic assumptions collapse with it. Our intuitions about time, about causality, about what it even means for something to exist. We are used to thinking of time as a line that starts somewhere and moves forward. But that picture may be a feature of human experience, not a feature of reality. In modern physics, time behaves very differently than our instincts suggest. In some theories, it may not be fundamental at all. In others, it may emerge from deeper structures. In still others, the question of a first moment may simply be meaningless. When we say before the Big Bang, we may be asking a question that has no answer, not because it is mysterious, but because it is malformed. Like asking what is north of the North Pole. The problem is not that we lack imagination. The problem is that our language carries assumptions that reality does not share. The phrase, the beginning of the universe, sounds precise. It sounds scientific, but it smuggles in an idea that may not survive careful scrutiny. This is why physicists speak cautiously, why they hedge their claims, why they say, as far as we can tell, and within the limits of our models. The universe does not announce its origins clearly. It leaves us clues, expansion, radiation, structure, but it does not tell us where the story truly starts. And that raises a disturbing possibility. What if the universe has no beginning in the sense we imagine? What if the Big Bang is not the start of time, but a transition? What if asking why there is something rather than nothing is the wrong question altogether? These are not philosophical speculations layered on top of science. They emerge directly from taking the science seriously. In this video, we will be careful. We will separate what is known from what is assumed, what the Big Bang explains from what it does not, where physics speaks confidently and where it falls silent. By the end, you will understand why the Big Bang is one of the most successful scientific theories ever developed, and why it does not tell us that the universe had a beginning. And once you see that distinction clearly, the universe starts to look very different. Let us begin by examining where the familiar story came from, and why it is so compelling even if it may not be true. The familiar story of the Big Bang did not emerge fully formed. It evolved gradually, shaped as much by human intuition as by observation. In the early 20th century, the dominant assumption among scientists was that the universe was static, eternal, unchanging on the largest scales. This belief was not grounded in strong evidence, but in philosophical comfort. An eternal universe required no explanation for its origin. It simply was. Even Albert Einstein initially favored this picture. When he first wrote down the equations of general relativity in 1915, they did not naturally allow for a static universe. Gravity would cause matter to clump together, pulling the cosmos inward. To counteract this, Einstein introduced an additional term into his equations, the cosmological constant, designed specifically to hold the universe in balance. This was not a prediction. It was an adjustment. Then, in the 1920s, observations began to undermine the static picture. Edwin Hubble and others discovered that distant galaxies were moving away from us. More precisely, space itself appeared to be expanding. The farther away a galaxy was, the faster it receded. This was not motion through space. It was the stretching of space itself. Suddenly, the universe was no longer timeless and fixed. It was dynamic, evolving, changing. If space is expanding today, then in the past it must have been smaller, denser, hotter. This realization led to a powerful insight. The universe has a history. But here is where a subtle shift occurred. A shift that still shapes how the Big Bang is misunderstood today. From the fact that the universe was denser in the past, it was tempting to imagine rewinding the cosmic movie all the way back to a single instant. A moment when everything was compressed into an infinitely small point. A moment of creation. This image was compelling. It felt like a beginning. It matched our instincts. But it was never something the theory itself demanded. The equations of cosmology describe how the universe evolves as it expands. They do not describe how it comes into existence. They tell us how distances between points in space change over time. They tell us how temperature and density evolve. They do not contain a mechanism for creation. The Big Bang theory, properly understood, is a theory of expansion, not of origin. The problem is that language often blurs this distinction. When scientists say the universe was once extremely hot and dense, it is easy to hear that as saying everything began in that state. But once does not necessarily mean at the beginning. It simply means earlier than now. The moment where density and temperature appear to diverge to infinity is not a prediction of physical reality. It is the point where the mathematical description breaks down. This is a crucial idea, and it is one that appears throughout physics. When classical physics predicted that atoms should collapse, the solution was not that atoms truly collapse. The solution was quantum mechanics. When classical electromagnetism predicted infinite energy emission at short wavelengths, the solution was not that energy becomes infinite. It was a new theory. Infinities are not discoveries. They are warning signs. They tell us that a model has been pushed beyond its domain of validity. Yet in popular accounts, the infinity at the beginning of cosmological equations is often treated as a literal feature of the universe. A real moment of infinite density. A true beginning of time. This interpretation persists not because it is scientifically solid, but because it is narratively satisfying. Beginnings feel necessary. Stories demand them. But the universe is not obligated to tell a story we recognize. To understand why the idea of a beginning is so persistent, we have to look at how human intuition works. We experience time locally, sequentially, one moment following another. Everything we encounter begins at some point and ends at another. Stars form. People are born. Civilizations rise and fall. It feels natural to extend this pattern to the universe itself. But physics has taught us repeatedly that intuition built from everyday experience does not scale to cosmic or quantum regimes. Space and time behave in ways that violate common sense. Objects contract as they move faster. Time slows down in strong gravitational fields. Events that are simultaneous for one observer are not simultaneous for another. In this context, assuming that the universe must have begun in the same way familiar objects begin is not cautious reasoning. It is projection. When physicists talk about the Big Bang as a beginning, they are often speaking loosely, using shorthand, compressing complex ideas into accessible language. This is understandable, but it comes at a cost. The cost is clarity. The Big Bang does not describe a moment when time itself started ticking. It describes a regime where our current understanding of time ceases to be reliable. Those are not the same thing. Imagine standing at the edge of a map. Beyond that edge, the paper is blank. The blank space does not mean the land ends there. It means the map does. Cosmological equations are maps of reality. Extremely successful ones. But like all maps, they have limits. The Big Bang marks the edge of the map, not the edge of existence. This distinction becomes even more important when we consider how time itself is treated in modern physics. In relativity, time is not a universal background flowing independently of the universe. It is intertwined with space, a dimension that depends on motion and gravity. Time behaves differently for different observers. There is no single, absolute clock ticking away for the universe as a whole. This already complicates the idea of a universal, first moment. If time is part of the universe, not something outside it, then asking what happened before time began may be incoherent. Not mysterious. Incoherent. It may be like asking what existed before space existed, or what direction lies beyond the end of direction. These are not unanswered questions. They are category errors. Yet they feel meaningful because language encourages us to ask them. The phrase, "the beginning of the universe," suggests a transition from non-existence to existence. From nothing to something. But the Big Bang Theory does not describe such a transition. It does not describe nothing. It describes a hot, dense state governed by physical laws. And physical laws presuppose a framework in which they operate. This raises a subtle but profound point. If the Big Bang is described by equations, then something must already exist for those equations to apply to. The equations do not describe creation. They describe evolution. This is why many physicists are careful to say that the Big Bang was not the beginning of the universe, but the beginning of our description of the universe. There is a difference. The problem is not that science lacks imagination. The problem is that science insists on precision. And precision often strips away the dramatic certainty that popular narratives rely on. It is tempting to say, the universe began with the Big Bang, because it sounds simple. It feels final. It closes the question. But the honest scientific position does not close the question. It reframes it. Instead of asking, what happened at the beginning of the universe? Physics asks, what does our best theory actually describe, and where does it stop working? This is a more difficult question, and a more unsettling one, because it forces us to confront the possibility that the universe does not have the kind of beginning we intuitively expect. That possibility will guide everything that follows. Before we explore alternative models and deeper theories, we must fully understand what the Big Bang does and does not claim. Without that clarity, every discussion of cosmic origins becomes confused. The myth of a cosmic beginning is powerful precisely because it sits at the intersection of science, intuition, and narrative. It borrows the authority of physics, the familiarity of human experience, and the structure of a story. But authority, familiarity, and narrative coherence are not guarantees of truth. To move forward, We must let go of the assumption that the universe must conform to our expectations of beginnings and endings. We must be willing to follow the evidence and the limits of the evidence wherever they lead. Only then can we ask better questions. Only then can we understand why the Big Bang is real and why the beginning of the universe may not be. There is another reason the idea of a beginning has been so difficult to let go of, and it has less to do with physics than with psychology. A universe with a beginning feels explainable. A universe without one feels unsettling. If everything began, then we can imagine a cause. If there was a first moment, then we can imagine a reason for that moment. But if the universe did not begin in any ordinary sense, then the familiar chain of explanation breaks down. We are forced to confront a reality that does not fit neatly into cause and effect stories. This discomfort often gets mistaken for a scientific problem. In truth, it is a human one. Physics does not promise comfort. It promises consistency with observation. And observation tells us something surprisingly limited about the early universe. We see evidence that the universe was once hot and dense. We see how matter clumped into galaxies. We see faint radiation left over from an earlier phase. But all of this evidence points to a period of evolution, not a moment of creation. The farther back we look, the less confident our descriptions become. This is not because the universe becomes more mysterious, but because our tools become less reliable. Telescopes cannot see beyond certain distances. Signals cannot reach us from beyond certain horizons. And equations built for one regime of physics begin to fail when applied to another. The Big Bang sits at the intersection of extraordinary success and unavoidable limitation. It explains an enormous range of observations with remarkable precision. And yet, when pushed to its extreme, it reveals the boundary of its own applicability. This dual nature is often lost in simplified explanations. Popular accounts tend to treat the Big Bang as a dramatic event, a flash of creation, because events are easier to visualize than boundaries. But a boundary is not an event. It is a limit, and limits are not failures. They are signposts. In science, a theory that clearly indicates where it stops working is more valuable than one that pretends to answer everything. The Big Bang theory does exactly that. It tells us, with mathematical clarity, how far we can reliably speak about the universe's past and where our confidence ends. This is why careful cosmologists avoid saying that the Big Bang was the beginning of time. They say instead that it marks the earliest moment we can describe using our current models. That difference may sound subtle. It is not. To say, this is the beginning, is to make a claim about reality. To say, this is the limit of our description, is to make a claim about knowledge. Confusing the two leads to profound misunderstandings. The universe does not announce when our theories stop working. It does not place a sign at the edge of applicability. It simply behaves as it does. The responsibility lies with us to recognize when our mathematical tools are being stretched beyond their design. This recognition is not a weakness of science. It is one of its greatest strengths. Historically, the most important breakthroughs in physics have come not from answering questions, but from realizing which questions were being asked incorrectly. The failure of classical mechanics to describe atomic stability did not mean atoms were impossible. It meant the question had to be reformulated. The same is true here. The question, what happened at the beginning of the universe, assumes there was a beginning in the sense the question implies. Physics does not confirm that assumption. It challenges it. This challenge is not an invitation to speculation without restraint. It is an invitation to humility, to acknowledge that some of our most cherished intuitions may not survive contact with reality. In the sections that follow, we will examine what the Big Bang actually tells us, and what it leaves unresolved. We will see why the theory is one of the great achievements of human understanding, and why it cannot, by itself, answer the deepest questions we want to ask. We will also see why insisting on a beginning may be less scientifically grounded than accepting uncertainty. The universe does not owe us an origin story. It owes us consistency with observation. And observation, when interpreted carefully, tells a story that is far more subtle and far more interesting than a simple moment of creation. The Big Bang is real. Its evidence is everywhere. But the idea that it marks the beginning of everything is not something the universe has told us. It is something we have inferred, and perhaps inferred too much. With that distinction clearly in mind, we are now prepared to move forward. Only once we understand what the Big Bang truly describes can we begin to explore what lies beyond it, not in imagination, but in physics. To understand what the Big Bang actually describes, we have to let go of one of the most persistent images in popular science, the idea of an explosion. The Big Bang was not an explosion in space. There was no center, no outward blast, no surrounding emptiness into which matter expanded. This misconception is so common that it is difficult to overstate how deeply it distorts understanding. An explosion happens at a location. It sends material outward from a point into pre-existing space. Shrapnel flies away from a center. The farther you are from that center, the later the shockwave reaches you. The Big Bang was nothing like this. The Big Bang describes the expansion of space itself, everywhere at once. When cosmologists say the universe is expanding, they do not mean that galaxies are rushing outward through a static void. They mean that the distances between galaxies increase because the fabric of space between them stretches. There is no central point from which everything moves away. From the perspective of any galaxy, all sufficiently distant galaxies appear to be receding. Every location can legitimately describe itself as being at the center of the expansion. This is not an interpretation. It is a direct consequence of the mathematics of general relativity. Once this is understood, many familiar questions dissolve. What did the universe expand into? Where did the explosion happen? These questions assume a background space that existed before the Big Bang. The theory does not include such a background. Space is part of what is evolving. The Big Bang theory begins not with an explosion, but with a statement about geometry. The universe has been expanding from a denser state. This statement is not philosophical. It is observational. In the early 20th century, Edwin Hubble and others measured the spectra of distant galaxies and discovered something remarkable. The light from these galaxies was systematically shifted toward longer wavelengths, a phenomenon known as redshift. The farther away a galaxy was, the greater the redshift appeared to be. This relationship was not random. It was proportional. Distance and redshift were connected. The simplest explanation was that space itself was expanding, stretching the wavelengths of light as it traveled. This interpretation was later placed on a firm theoretical footing within general relativity. Expansion was no longer speculation. It was measurable. Once expansion is accepted, a powerful inference follows. If the universe is expanding today, then in the past it must have been smaller. If it was smaller, matter and energy were more concentrated. Temperatures were higher. Densities were greater. This inference does not rely on exotic assumptions. It follows directly from reversing the observed expansion. The Big Bang theory, at its core, is simply this extrapolation. The universe evolves, and if we run that evolution backward, we reach a hot, dense early state. Nothing in this statement requires a beginning. It requires only change. One of the strongest pieces of evidence for this picture is the cosmic microwave background, often abbreviated as the CMB. The CMB is sometimes described as the afterglow of the Big Bang. That description is not wrong, but it is incomplete. In the early universe, conditions were so hot that atoms could not exist. Electrons and atomic nuclei formed a plasma that scattered light constantly. Photons could not travel freely. The universe was opaque. As the universe expanded and cooled, it eventually reached a temperature low enough for electrons to bind to nuclei, forming neutral atoms. At that moment, light was finally able to travel long distances without being scattered. That light has been traveling ever since. As space expanded, its wavelength stretched. What was once high-energy radiation became microwave radiation. Today, we observe it as a nearly uniform background glow filling the entire sky. This radiation does not come from a single direction. It comes from everywhere. It is astonishingly uniform, differing in temperature by only tiny fractions of a degree across the sky. These small variations encode information about the seeds of galaxies and large-scale structure. The existence of the cosmic microwave background is not controversial. It is one of the most precisely measured phenomena in all of science. Satellites such as COBE, WMAP, and Planck have mapped it in extraordinary detail. What does this tell us? It tells us that the universe really was once hot and dense. It tells us that there was a time when matter and radiation were tightly coupled. It tells us that the universe has been expanding and cooling for billions of years. But it does not tell us that this was the beginning. The cosmic microwave background does not represent the first moment of time. It represents the earliest moment we can see. There is a crucial difference. Looking at the CMB is like seeing the surface of a fog bank. Beyond it, light cannot reach us. That does not mean nothing exists beyond the fog. It means our vision stops there. The Big Bang Theory describes everything from that foggy surface forward. It does not describe what lies beyond.
This is completely
Another
unacceptable.
key idea often misunderstood is the phrase
I won't
hot
stand
and
for it.
dense. These words suggest compression, as if matter were being squeezed into a small region of space. But this is misleading. The early universe was not hot and dense because matter was being crushed inward. It was hot and dense because space itself was smaller. There was no center toward which things collapsed. The entire universe was in a state where distances between all points were shorter. Temperature, in this context, is a measure of average energy per particle. In a smaller universe, particles interact more frequently. Energies are higher. Conditions are more extreme. As space expands, interactions become less frequent. Energies drop. The universe cools. This cooling is not caused by energy leaking away. It is caused by expansion. Understanding this removes another common misconception, that the early universe was a tiny ball sitting somewhere in space. It was not. If the universe is infinite today, it was infinite then. If it is finite today, it was finite then. Expansion does not require a change in overall extent. It requires only a change in scale. This brings us to an important point that often goes unappreciated. The Big Bang Theory does not tell us whether the universe is finite or infinite. Both possibilities are compatible with the observations. A universe can be expanding and hot in the past whether it is spatially finite or infinite. The theory describes how distances change, not how large the universe is in total. When people imagine the universe emerging from a point, they are imagining something the theory does not say. That image comes from pushing the equations beyond their reliable range. If we continue extrapolating backward, temperatures rise, densities increase, and eventually the mathematics predicts a breakdown. Physical quantities diverge. The theory stops giving sensible answers. This breakdown is often labeled the Big Bang singularity. But this label can be misleading. The breakdown does not occur because the universe reaches a special physical state that we understand. It occurs because the equations we are using are no longer adequate. General relativity treats space-time as smooth and continuous. At extremely high energies and small scales, this assumption is expected to fail. Quantum effects should become important. Yet the Big Bang equations do not include a quantum description of space-time. They are classical equations being applied where classical physics should not be trusted. What the Big Bang Theory actually gives us, then, is not a story of creation, but a remarkably successful description of cosmic evolution over a vast range of time. From fractions of a second after the early hot phase, through the formation of nuclei, atoms, stars, galaxies, and cosmic structure, the theory works extraordinarily well. Its success is not diminished by the fact that it has limits. In fact, its limits are precisely what tell us how far we have truly understood. At this stage, we can summarize what the Big Bang does and does not claim. It claims that the universe has been expanding. It claims that the universe was once hotter and denser. It claims that the large-scale structure we see today evolved from small initial variations. It does not claim that the universe came from nothing. It does not claim that time began at a particular moment. It does not claim to describe the ultimate origin of existence. Those claims are often added afterward, sometimes unconsciously, by the way the story is told. Recognizing this difference is essential because it prepares us for the deeper question that lies ahead. What happens when we try to push the Big Bang Theory beyond where it applies? That question will take us to the very edge of what physics can currently say. And that is where things become truly interesting. Up to this point, everything we have discussed rests on solid observational ground. Expansion is measured. The cosmic microwave background is observed. The cooling history of the universe is reconstructed with remarkable precision. But as we move earlier in cosmic history, something important changes. Our confidence begins to narrow. The Big Bang Theory works extremely well from a fraction of a second after the early hot phase onward. But when cosmologists attempt to describe the universe at even earlier times, they encounter puzzles that the basic Big Bang model alone cannot resolve. One of the most important of these puzzles concerns uniformity. The universe, on the largest scales, looks astonishingly similar in all directions. The temperature of the cosmic microwave background is nearly the same everywhere in the sky, even in regions that appear to have had no time to communicate with one another in the early universe. This is known as the horizon problem. If different regions of the early universe were never in causal contact, how did they end up with nearly identical properties? Another puzzle concerns geometry. Observations suggest that space is very nearly flat. This flatness is not generic. It requires extremely special initial conditions if the universe evolved according to the simplest expansion models. There is also the problem of relics. Certain hypothetical particles or defects predicted by high-energy theories are conspicuously absent from the observable universe. These puzzles do not invalidate the Big Bang Theory. They reveal its incompleteness. To address them, cosmologists proposed an extension to the standard picture known as cosmic inflation. Inflation is not an alternative to the Big Bang. It is an addition. The idea is that, very early in its history, the universe underwent a brief period of extremely rapid expansion. Space expanded exponentially, growing by an enormous factor in a tiny fraction of a second. During inflation, regions that were once very close together were driven far apart. This explains why distant regions of the universe appear so similar today. They were once part of the same small, interacting region. Inflation also naturally explains why space appears nearly flat. Rapid expansion smooths out curvature, much like inflating a balloon makes a small patch of its surface appear flatter. Perhaps most importantly, inflation provides a mechanism for generating the tiny fluctuations observed in the cosmic microwave background. Quantum fluctuations, stretched to cosmic scales by inflation, become the seeds of galaxies and large-scale structure. These successes have made inflation an extremely influential idea in modern cosmology. But here is the crucial point. Inflation does not solve the question of a beginning. It moves the boundary. Instead of asking what happened at the Big Bang, we now ask what happened before inflation. Instead of a single starting point, we introduce an earlier phase whose own origin remains unexplained. In some inflationary models, inflation ends locally but continues elsewhere, leading to what is called eternal inflation. In such scenarios, different regions of space stop inflating at different times, producing a vast, possibly infinite, multiverse of expanding regions. In these models, our observable universe is just one region among many. This idea is speculative, but it illustrates something important. As theories become more ambitious, the concept of a single cosmic beginning becomes harder to maintain. Even inflation, powerful as it is, does not give us a first moment. It pushes the question back. At this stage, it is tempting to say, let us simply extrapolate further. Let us run the equations backward through inflation and see what happens. This is where caution becomes essential. Extrapolation is not discovery. The equations used in cosmology are based on assumptions about space-time, matter, and energy. They work beautifully in regimes where those assumptions hold. But when densities approach extreme values, those assumptions become questionable. General relativity treats space-time as a smooth continuum. Quantum mechanics tells us that at sufficiently small scales, nature is not smooth at all. When we combine general relativity with ordinary matter and radiation, we can mathematically extrapolate backward to a point where density becomes infinite. But this procedure ignores quantum effects that are expected to dominate at those scales. The resulting singularity is not a prediction of new physics. It is a sign that known physics is being misapplied. This is why many physicists are careful to say that the Big Bang singularity is not a physical event. It is a boundary of the classical description. To see why this matters, consider an analogy. Imagine using the equations of fluid dynamics to describe water flowing through a pipe. These equations work extremely well on macroscopic scales. But if you attempt to apply them to individual molecules, they fail. The equations were never meant to describe that regime. If you insisted on extrapolating them anyway, you might obtain nonsensical results. But those results would not describe water's true microscopic behavior. They would describe the failure of the model. Cosmological singularities arise in exactly this way. They are produced by extending classical equations into a domain where quantum effects are expected to dominate. The Big Bang, understood properly, is not a moment when physics explains creation. It is the point where physics, as currently formulated, stops being able to answer questions. This distinction often gets blurred because of how the equations are presented. When density and temperature diverge mathematically, it is easy to mistake this divergence for a real physical state. But physics has taught us repeatedly that infinities are untrustworthy. Whenever a theory predicts infinite quantities, it is usually a sign that a deeper theory is needed. This insight reshapes how we think about the early universe. Instead of imagining a definite beginning, we are led to imagine a boundary, a surface beyond which our current description does not extend. That boundary may correspond to something real and physical. But whatever it is, it cannot be adequately described by the equations that produce the singularity. This brings us to a subtle but important point. The Big Bang theory is extraordinarily successful within its domain. It explains the expansion of the universe, the formation of light elements, the cosmic microwave background, and the growth of structure. Its success does not require it to explain everything. The demand that it explain the ultimate origin of the universe is an additional expectation, one rooted more in human curiosity than in scientific necessity. Science advances not by answering every question, but by knowing which questions it can legitimately address. At present, the question of a cosmic beginning lies at the edge of that legitimacy. The more carefully we examine the Big Bang theory, the clearer this becomes. Its equations describe evolution, not creation. Its evidence supports a hot, dense past, not a first moment. Its breakdown signals the need for new physics, not the discovery of a literal beginning. As we push closer to this boundary, the language we use becomes increasingly important. Words like origin, creation, and beginning carry assumptions that the theory itself does not support. Replacing them with more precise terms, such as early phase, boundary, or limit of applicability, may feel less satisfying, but it is more accurate. Accuracy matters, especially when discussing questions as fundamental as the nature of the universe itself. In the next section, we will confront this boundary directly. We will examine what happens when physics can no longer give reliable answers, and why the concept of a beginning may need to be abandoned altogether. At this point, a pattern should be becoming clear. Every time we push the Big Bang theory closer to what we intuitively call the beginning, the theory does not give us firmer answers. It gives us warning signs. Those warning signs take the form of infinities, breakdowns, and unanswered questions. Not because the universe becomes chaotic or unknowable, but because the framework we are using reaches the edge of its validity. This is not unique to cosmology. It is how physics has always progressed. Classical mechanics fails at atomic scales. Classical electromagnetism fails for black-body radiation. In each case, the failure did not mean nature was inconsistent. It meant the theory was incomplete. The Big Bang theory, when treated carefully, fits this same pattern. It tells us that the universe has been expanding from a hot, dense state. It tells us how temperatures dropped, how particles formed, how structure emerged. It does all of this with extraordinary precision. But when we ask what happened at the very earliest times, when densities approach extreme values and space-time curvature becomes enormous, the theory stops speaking reliably. This silence is often mistaken for an answer. The phrase, "the universe began at the Big Bang," sounds like a conclusion, but it is actually a placeholder. It fills the gap where explanation ends. To understand why, we need to look more closely at what happens when we push the equations to their limit. As we extrapolate backward, physical quantities such as temperature and density grow without bound. Eventually, they diverge to infinity. This mathematical divergence is what is commonly labeled the Big Bang singularity. But this singularity is not something we observe. It is not something we measure. It is not something we test. It is a feature of a calculation. And calculations are only as trustworthy as the assumptions that go into them. The equations used in standard cosmology combine general relativity with simple descriptions of matter and radiation. They assume spacetime is smooth and continuous. They ignore quantum effects on spacetime itself. These assumptions work extraordinarily well over a vast range of conditions. But there is no reason to believe they remain valid arbitrarily far back in time. In fact, there is strong reason to believe they do not. At sufficiently high energies and small scales, quantum effects are expected to dominate. Space-time itself may behave in ways that classical equations cannot capture. Concepts like distance, duration, and even causality may require revision. When classical equations produce infinities, physics does not interpret this as reality becoming infinite. It interprets it as a signal that new physics is needed. This is why many cosmologists emphasize that the Big Bang singularity is not a physical event. It is a boundary marking the breakdown of the classical description. Once this is understood, the idea of a cosmic beginning becomes far less certain. A beginning implies a moment when something came into existence. But the Big Bang equations do not describe such a moment. They describe a regime where our ability to describe evolution ends. There is a profound difference between saying, "This is where the universe began," and saying, "This is where our theory stops working." The first is a claim about reality. The second is a claim about knowledge. Confusing the two leads to unnecessary metaphysical conclusions. It also leads to misguided questions. When people ask, "What caused the Big Bang?" they are often assuming that the Big Bang was an event that required a cause in the usual sense. But if the Big Bang marks a boundary of description rather than an event within time, then the question of cause may not apply. Causation, as we understand it, operates within time. Causes precede effects. But if time itself is part of what becomes ill-defined near this boundary, then applying ordinary causal language may be inappropriate. This does not mean that there is no explanation. It means the explanation may not resemble what we expect. At this boundary, familiar concepts begin to lose their footing. Time may not be fundamental. Space may not be continuous. The distinction between past and future may blur. These are not philosophical speculations added from outside physics. They are implications drawn from taking existing theories seriously and recognizing their limits. This is why modern cosmology increasingly speaks in terms of boundaries rather than beginnings. A boundary does not require a before in the usual sense. It marks the limit of a particular description. Beyond it, a different description may apply. We have already encountered this idea in another context. The surface of last scattering, the origin of the cosmic microwave background, is not the beginning of the universe. It is the earliest time from which light can reach us. It is an observational boundary. Similarly, the Big Bang singularity may be a theoretical boundary, the earliest time our current equations can describe. This perspective reframes the entire discussion. Instead of asking why the universe began, we ask why our theories describe the universe the way they do, and what needs to change for them to describe earlier phases. This shift may feel unsatisfying, but it is intellectually honest. Science does not fill gaps with stories. It marks them clearly. And here, the gap is unmistakable. The Big Bang theory, as successful as it is, does not tell us whether the universe had a beginning. It tells us that our description of the universe has a limit. That limit may correspond to something physically meaningful. It may correspond to a transition, a bounce, a phase change, or something else entirely. But whatever it is, it cannot be described by simply extending classical equations. This realization has motivated decades of research into new frameworks, approaches that attempt to describe spacetime itself quantum mechanically. These efforts are ongoing. They are incomplete. And they are deeply challenging. But they are driven by a clear recognition. The Big Bang, as commonly described, is not the final word on cosmic origins. It is the starting point of a deeper inquiry. When this is understood, the phrase, the beginning of the universe, begins to look less like a discovery and more like a misunderstanding. The universe may have a beginning. It may not. What we can say, with confidence, is that the Big Bang theory does not settle the question. And that brings us to an important conclusion. The Big Bang is one of the greatest achievements in the history of science. It explains an enormous range of phenomena with remarkable consistency. It has survived decades of observational testing. Its greatness does not lie in providing a simple origin story. It lies in revealing how much we can know and how much remains unknown. Recognizing this does not weaken science. It strengthens it. It replaces false certainty with genuine understanding. And it prepares us for the next stage of the discussion, where we will explore what physics proposes beyond this boundary, not as speculation, but as carefully constructed attempts to extend our understanding where classical descriptions fail. Before we move on, let us pause and take stock. The Big Bang describes expansion, not explosion. It describes evolution, not creation. It describes a hot, dense past, not a first moment of time. Where the equations break down, they do not reveal a beginning. They reveal the edge of our current knowledge. That edge is not the end of the story. It is the place where the next story begins. At some point, every scientific theory encounters a boundary. Not a dramatic collapse. Not a sudden failure. But a quiet moment where the equations stop being trustworthy. This is the moment we have now reached in our discussion. Up to this point, the Big Bang theory has guided us with extraordinary success. It has described the expansion of the universe, the cooling of matter and radiation, the formation of structure, and the cosmic microwave background with astonishing accuracy. But when we push the theory further back, when we try to describe the universe at the earliest conceivable times, something fundamental changes. The equations still produce answers. But those answers stop meaning what we think they mean. This is where physics stops answering questions in the way we are used to. And it is crucial to understand why. The mathematical framework behind modern cosmology is general relativity. Einstein's theory treats gravity not as a force, but as the curvature of spacetime caused by mass and energy. Objects follow paths determined by this curvature. General relativity is one of the most successful theories ever developed. It has passed every experimental test thrown at it, from the orbit of Mercury to gravitational waves detected a century after its prediction. But general relativity has a hidden assumption. It assumes that spacetime is smooth and continuous. This assumption works extraordinarily well on large scales. But there is no reason to believe it remains valid at arbitrarily small scales or arbitrarily high energies. When cosmologists apply general relativity to the early universe, they do so knowing this assumption may eventually fail. As they extrapolate backward, spacetime curvature increases. Energy densities rise. Length scales shrink. Eventually, they reach a regime where quantum effects cannot be ignored. Yet the equations being used contain no quantum description of spacetime itself. This mismatch is the source of the problem. As densities grow without bound in the equations, we encounter what is called a singularity. Physical quantities such as curvature and energy density diverge to infinity. This is often described as the Big Bang singularity. But this description is deeply misleading. A singularity in physics does not represent a place or moment we have discovered. It represents a breakdown of the mathematical model. When an equation returns infinity, it is not telling us that nature becomes infinite. It is telling us that the equation has been pushed beyond the conditions it was designed to handle. This distinction cannot be overstated. Physics has encountered this situation many times before. Classical electromagnetism predicted that an accelerating charge should radiate infinite energy under certain conditions. Classical statistical mechanics predicted infinite energy density for blackbody radiation at short wavelengths. In each case, the infinities were not features of reality. They were signs that a deeper theory was required. Quantum mechanics resolved these problems by replacing classical assumptions with new principles. The singularity in cosmology has the same status. It is not a physical event we should accept as real. It is a signal that classical general relativity is incomplete. Yet in popular accounts, this mathematical warning sign is often reinterpreted as a literal beginning of the universe. The infinite density predicted by the equations is treated as a real state of existence. This reinterpretation is not justified by the physics. To see why, consider what the equations are actually doing. They are describing how distances between points in space change over time. They are not describing the creation of those points. They are not describing the emergence of spacetime itself from nothing. When the equations fail, they fail precisely at the point where such questions would require new physics. Calling this failure a beginning does not explain it. It labels it. And labels are not explanations. At this boundary, even the concept of time becomes problematic. In general relativity, time is not an independent parameter ticking away uniformly throughout the universe. It is part of the geometry of spacetime. It depends on motion, gravity, and the distribution of energy. Near the singularity, spacetime curvature becomes extreme. The very structure that allows us to define time intervals begins to break down. This raises a subtle but profound issue. If time itself becomes ill-defined, then the idea of a first moment loses its meaning. Moments are ordered by time. Beginnings require time. If the framework that defines time no longer applies, then asking about the first moment may be like asking about the first point north of the North Pole. It is not that we do not know the answer. It is that the question assumes something that is no longer valid. This is why many physicists are cautious when speaking about the beginning of time. The phrase sounds precise, but it hides an assumption that may not survive closer scrutiny. Time, as we experience it, may be an emergent concept, something that arises from deeper physical processes rather than existing at the most fundamental level. If this is the case, then time itself may have a domain of applicability, just like any other physical concept. Beyond that domain, the language of before and after may no longer apply. This is an uncomfortable idea, because it undermines one of the most basic structures of human thought. We think in terms of sequences. We explain things by tracing them back to earlier causes. But the universe is not required to conform to the way our minds organize experience. At the boundary where physics stops answering in familiar ways, our intuitions fail us. This does not mean we have reached the end of explanation. It means we have reached the end of a particular explanatory framework. The singularity is not the place where physics breaks down. It is the place where classical physics admits its limits. And that admission is not a weakness. It is an act of intellectual honesty. Rather than pretending to know what happens at the boundary, physics tells us plainly, our current theories cannot answer this question. This honesty is what distinguishes scientific uncertainty from ignorance. Ignorance fills gaps with stories. Science marks gaps and seeks better tools. In the next section, we will examine how physicists interpret this boundary. We will explore why the phrase, "we do not know," is not a failure, but a necessary step toward deeper understanding. Because what lies beyond this boundary is not nothing. It is simply something we do not yet know how to describe. When physicists say, "we do not know," it is often misunderstood. Outside of science, not knowing is usually treated as a problem to be hidden. A sign of weakness. An admission that something has gone wrong. In physics, it means something very different. It means that a question has been pushed to the edge of what a theory can legitimately answer. This distinction matters deeply in cosmology, because the question of a cosmic beginning sits precisely at such an edge. When asked whether the universe had a beginning, physicists do not hesitate because they lack intelligence or imagination. They hesitate because they recognize the limits of the tools they are using. Those tools, general relativity and quantum field theory, work extraordinarily well within their domains. But they are not yet unified. And near the earliest moments of cosmic history, both are required simultaneously. This creates a situation unlike most others in science. Normally, when a theory fails, we know which theory should replace it. Classical mechanics gives way to quantum mechanics. Newtonian gravity gives way to general relativity. Here, we do not yet have the replacement. We know that general relativity cannot be trusted arbitrarily far back. We know that quantum effects must matter. But we do not yet have a complete, experimentally confirmed theory of quantum gravity. This is not speculation. It is a well-recognized gap. And it explains why cosmologists speak cautiously about the beginning of the universe. The phrase, "we do not know," does not mean there is no answer. It means we do not yet have a framework capable of providing one. This is a crucial difference. Science does not progress by pretending to know more than it does. It progresses by identifying precisely where knowledge ends. The boundary marked by the Big Bang singularity is one such place. It tells us that extrapolating classical equations backward leads to nonsense, infinities that cannot correspond to physical reality. It tells us that new principles are required, but it does not tell us what those principles are. At this boundary, even the most basic concepts begin to lose clarity. Time, which we treat as fundamental in everyday experience, may not exist in the same way at extreme scales. Space, which we imagine as a continuous arena, may be composed of discrete structures. Causality, which underlies all ordinary explanations, may not apply in its usual form. These are not radical claims made lightly. They arise because the mathematical structures we rely on no longer behave sensibly. When space-time curvature becomes extreme, when energy densities approach theoretical limits, the smooth picture of space-time begins to fracture. This is not an aesthetic problem. It is a technical one. General relativity describes how space-time curves, but it does not describe how space-time itself behaves at the smallest scales. Quantum mechanics describes particles and fields, but it assumes a fixed space-time background. Near the Big Bang boundary, neither description is sufficient on its own. This leaves us in a rare position. We know enough to see that our theories fail, but not enough to see what replaces them. This is why physicists resist confident statements about the universe's ultimate origin. It is tempting to fill the gap with certainty, to say that time began, or that the universe emerged from nothing, or that a singularity is physically real. But these statements go beyond what the evidence supports. They are not conclusions drawn from theory. They are narratives imposed on uncertainty. The honest position is more restrained and more difficult to accept. It says, we can describe the universe back to an extremely early phase. We can measure the remnants of that phase. We can test our models against observation with extraordinary precision. But when we ask what lies beyond that phase, whether there was a first moment, whether time itself emerged, whether the universe has an origin at all, we step beyond what current physics can answer. This does not mean the question is meaningless. It means the answer is not yet accessible. And that distinction is essential. Some questions are meaningless because they are ill-posed. Others are meaningful but unanswered because the necessary conceptual tools do not yet exist. The question of a cosmic beginning may belong to the second category. Understanding this prevents a common mistake, confusing scientific humility with philosophical evasion. Physicists do not avoid the question of origins because it is uncomfortable. They avoid answering it definitively because doing so would require assumptions they cannot justify. This restraint is part of what makes science reliable. History provides many examples of what happens when this restraint is ignored. When early physicists insisted that atoms must obey classical laws, they reached contradictions. When astronomers insisted on circular planetary orbits because they seemed perfect, they complicated their models unnecessarily. Progress came not from defending intuition, but from abandoning it when evidence demanded. The question of the universe's beginning demands the same discipline. Our intuition tells us that everything must start somewhere, that there must be a first moment, a first cause. But intuition is not evidence. And in extreme regimes, intuition is often wrong. This is why the phrase, "the universe began with the Big Bang," is treated with caution by those who work in the field. It is not that the phrase is entirely false. It is that it oversimplifies a situation that is profoundly subtle. It takes a boundary of description and turns it into a statement about reality itself. This transformation may be emotionally satisfying, but it is not scientifically justified. At the edge of our knowledge, precision matters more than comfort. Saying "we do not know" preserves that precision. It keeps the question open without pretending to close it. It acknowledges limits without surrendering curiosity. And it creates space for future understanding. This openness is not passive. It actively guides research. The recognition that classical cosmology fails near the Big Bang has motivated decades of work in quantum gravity. Researchers are exploring radically new ways of describing spacetime. Approaches in which time may emerge, space may be quantized, and singularities may be replaced by finite structures. These efforts are difficult, abstract, and incomplete. But they are driven by a clear recognition of where current theories fall silent. Without that recognition, there would be no reason to search for deeper explanations. So when physicists say, "we do not know," they are not closing the book. They are marking the page where the next chapter must begin. This is why it is misleading to treat the Big Bang as the final answer to the question of origins. It is an answer to a different question. It tells us how the universe evolved from an early hot state. It does not tell us why that state existed, or whether it was the first of its kind. Those questions lie beyond the boundary of current physics. And acknowledging that boundary is not an admission of defeat. It is the most honest thing science can say. In the next section, we will confront the deepest implication of this boundary, that the concept of a beginning itself may be a human construct, not a fundamental feature of reality. There is a moment in every serious scientific investigation where the problem is no longer the lack of data, but the structure of the question itself. This is that moment. Up to now, we have assumed something so deeply ingrained that it rarely gets questioned. That the universe must have a beginning in the way stories have beginnings. A first moment. A starting point. A transition from nothing to something. This assumption feels natural because human experience is built around sequences. Birth precedes life. Causes precede effects. Every story we tell begins somewhere. But nature is not required to respect the narrative habits of the human mind. And when we examine the question of cosmic origins closely, something strange begins to emerge. The problem may not be that we do not know when the universe began. The problem may be that when itself stops making sense. To see why, we must take a step back and examine how time actually functions in modern physics. In everyday life, time feels absolute. A universal flow that moves forward independently of everything else. But this intuition is wrong. In Einstein's relativity, time is not an external parameter. It is part of spacetime itself. It stretches, contracts, and behaves differently depending on motion and gravity. There is no single cosmic clock ticking uniformly across the universe. Time is local, contextual, dependent on physical conditions. This already complicates the idea of a universal beginning. If time itself is part of the physical system, then asking what happened before time may be like asking what lies north of the North Pole. The question assumes a structure that may not exist. Near the Big Bang boundary, space-time curvature becomes extreme. The very geometry that defines temporal order begins to lose coherence. The equations that normally allow us to measure durations and intervals stop functioning reliably. This suggests something deeply unsettling. Time, as a meaningful concept, may only exist after a certain phase of cosmic evolution. If this is true, then the universe may not have begun in time. Time may have begun with the universe. But even that phrasing may be misleading. Because began still implies a moment. And a moment requires time. This circularity hints at a deeper problem. Perhaps the universe did not begin at all, at least not in the sense we usually mean. Perhaps the universe exists in a way that does not admit a first instant. This idea is difficult to accept, not because it is incoherent, but because it violates our intuitive expectations. We are used to thinking of existence as something that starts. But physics has repeatedly shown that intuition is a poor guide at fundamental scales. Consider another example. In quantum mechanics, particles do not have definite positions until measured. Asking where a particle really is before measurement assumes a classical property that does not exist. The question is not unanswered. It is malformed. Similarly, asking when the universe began may assume a temporal framework that only exists after certain physical conditions are met. If time is emergent rather than fundamental, then it may not make sense to apply it to the deepest level of reality. This is not philosophy replacing physics. It is physics forcing philosophy to change. Several modern approaches to quantum gravity take this idea seriously. In some formulations, time does not appear at the most fundamental level of the equations. The laws describe relationships between physical quantities without referring to a universal time parameter. Time emerges only approximately, in certain regimes, when systems behave in specific ways. If this is correct, then the universe's earliest description may not involve time at all. There would be no before the universe. Not because nothing existed, but because before was not a meaningful concept. This radically alters how we should think about origins. Instead of asking how the universe began, we may need to ask how time itself emerged. And that is a very different question. Some cosmological models explore this possibility explicitly. In certain quantum gravity-inspired scenarios, the universe does not originate from a singular point in time, but from a timeless quantum state. From this state, classical spacetime, with its familiar notion of time, emerges gradually. In such models, asking what happened before the Big Bang is like asking what happens before a phase transition. There is no sharp boundary, no first tick of a clock, only a change in the way reality behaves. Other models suggest cyclic or bouncing universes, where contraction precedes expansion. But even here, the concept of a beginning is slippery. If each cycle contains its own internal time, but the underlying description is timeless, then there may be no absolute starting point. The universe may not be a story with a first chapter. It may be a structure without an edge. This idea does not deny the Big Bang. It reframes it. The Big Bang becomes not the birth of existence, but the earliest phase of the universe that our current theories can describe. A boundary of knowledge, not a boundary of reality. This distinction matters enormously. When popular science claims that the Big Bang explains the origin of everything, it conflates two very different ideas. The Big Bang explains why the universe looks the way it does today. It does not explain why there is a universe rather than nothing. Those are separate questions. And treating them as the same leads to confusion. Physics excels at describing transformations within reality. It struggles when asked to explain why reality exists at all. That does not mean the latter question is illegitimate. It means it may not be answerable using the same tools. This realization has led many physicists to adopt a more careful language. Instead of saying the universe had a beginning, they say our description of the universe has a boundary. Instead of saying time started, they say time becomes ill-defined. These are not evasions. They are clarifications. They reflect an understanding that our concepts are not guaranteed to apply universally. Just as classical concepts of position and momentum fail in quantum mechanics, classical concepts of time and causality may fail in quantum gravity. This forces a humbling conclusion. The deepest questions about the universe may not have answers that fit into human language easily. Not because the universe is mysterious by design, but because our cognitive tools evolved for survival, not for understanding space-time at the Planck scale. We want beginnings because beginnings make stories meaningful. But the universe does not owe us narrative satisfaction. It owes us only consistency. And consistency, at the deepest level, may not include a beginning at all. This is why many physicists are comfortable saying something that sounds paradoxical at first. The Big Bang happened, but the universe may never have begun. The expansion occurred. The hot, dense phase existed. The cosmic microwave background was released. All of this is real. But treating that phase as the absolute start of existence may be a category error. It may be like treating the freezing of water as the beginning of matter. A change of state is not a creation event. The Big Bang may be the universe changing how it behaves, not coming into being. This perspective does not answer every question. It raises new ones. If time emerged, what governs the timeless regime? If space-time is not fundamental, what replaces it? If causality breaks down, how do explanations work? These are open questions. But they are better questions than the ones we started with. They do not assume what needs to be explained. They do not force reality into human metaphors. They accept uncertainty without surrendering rigor. And that is the hallmark of serious physics. As we move forward, it is important to hold two ideas simultaneously. First, the Big Bang is one of the most successful scientific theories ever developed. It explains an enormous range of observations with extraordinary precision. Second, the Big Bang does not explain the ultimate origin of the universe because the concept of an ultimate origin may not apply. These ideas are not in conflict. They describe different levels of understanding. The mistake is treating a boundary of theory as a boundary of reality. Once we stop making that mistake, the conversation changes. We stop asking how everything came from nothing. We start asking how our deepest concepts, time, space, causality, emerge from something more fundamental. That is a harder question, but it is also a more honest one. If the Big Bang is not the beginning of the universe, then an obvious question follows. What, if anything, replaces it? Not as a metaphor, not as a philosophical idea, but as a physical description of reality. This is where modern cosmology becomes both more cautious and more ambitious. Physicists do not claim to know what lies beyond the boundary where classical cosmology fails. But they also do not accept that the boundary represents the end of explanation. Instead, it marks the point where new theoretical tools are required. Over the past several decades, researchers have developed multiple approaches that attempt to extend our understanding beyond the Big Bang without treating it as a literal beginning of existence. None of these approaches is complete. None has been experimentally confirmed. But together, they reveal a consistent theme. The universe may not have begun. It may have transitioned. One of the most widely explored possibilities is that the Big Bang was not a creation event, but a phase change. In these models, the universe existed in some form prior to the hot, dense state described by standard cosmology. As conditions evolved, space-time entered a regime where its behavior changed dramatically, giving rise to the expansion we observe today. This idea appears in different guises, but the underlying logic is the same. When energy densities approach extreme values, classical general relativity becomes unreliable. Instead of predicting infinite curvature and a breakdown of physics, quantum effects are expected to intervene. Rather than collapsing into a singularity, the universe undergoes a transition. In some scenarios, this transition takes the form of a bounce. The universe contracts for an extended period, reaches a minimum size governed by quantum gravitational effects, and then begins to expand. The Big Bang is not the first moment of time, but the turning point between contraction and expansion. This does not mean the universe is cyclic in a simple or eternal sense. The details depend on the specific model. Some versions allow only a single bounce. Others allow multiple cycles. What matters is not the repetition, but the removal of the singular beginning. The Big Bang becomes a moment of extreme conditions, not a moment of creation. Another class of approaches challenges the idea that space-time itself is fundamental. In these frameworks, space-time emerges from deeper, non-spatiotemporal structures. Time and space are not the basic ingredients of reality. They are effective descriptions that become useful only under certain conditions. At the deepest level, the universe may be described by relationships between abstract quantities, quantum states, or informational structures that do not involve time in the usual sense. In such theories, the Big Bang does not mark the beginning of time. It marks the point where time becomes a meaningful concept. This distinction is subtle but crucial. If time emerges, then asking what happened before the universe is like asking what happens before temperature emerges in a cooling system. The concept does not apply until certain conditions are met. There is no first second of time, because seconds themselves are not fundamental. This radically alters the way we think about origins. Instead of imagining the universe springing into existence at a specific moment, we are invited to think of reality as existing in a more abstract form, gradually giving rise to spacetime, causality, and classical behavior. The Big Bang in this picture is not the start of existence. It is the start of the universe as we know it. Some models go further still. They suggest that the universe may be eternal in a direction that does not correspond to time as we experience it. There may be no global beginning or end, only different regimes with different effective descriptions. In these frameworks, the question of origin is replaced by the question of structure. Why does reality take the form it does? Why does space-time emerge at all? Why do the laws of physics have the form we observe? These are not questions about when something began. They are questions about why something has the structure it does. This shift in emphasis is not accidental. Physicists have learned, through experience, that insisting on familiar concepts at all scales leads to confusion. Classical ideas work well in classical regimes. Quantum ideas work well in quantum regimes. Expecting either to apply universally is a mistake. The Big Bang sits precisely at the boundary where this lesson becomes unavoidable. Every serious attempt to go beyond it weakens the idea of a singular beginning and strengthens the idea of a transition, an emergence, or a boundary of applicability. Importantly, these theories are not introduced to avoid uncomfortable questions. They are introduced because the mathematics demands them. When equations predict infinities, physicists do not interpret that as a discovery. They interpret it as a warning. The singularity is such a warning. It tells us that our classical description has reached its limit. It does not tell us what exists beyond that limit. Replacing the idea of a beginning with the idea of a boundary is therefore not philosophical speculation. It is a response to a technical problem. It reflects the same pattern seen throughout the history of physics. Newtonian mechanics failed at high speeds and strong gravity. Classical electromagnetism failed at atomic scales. In both cases, the resolution was not to insist on classical ideas, but to replace them with deeper frameworks. Modern cosmology is in a similar position. The Big Bang works extraordinarily well as a description of the early universe. But it does not and cannot describe the ultimate origin of everything. Recognizing this does not weaken the theory. It clarifies its scope. Theories that attempt to go beyond the Big Bang are not trying to erase it. They are trying to contextualize it. They treat it as the earliest phase of the universe that our current concepts can describe, not the absolute beginning of reality. This is why physicists speak carefully. They do not say the universe came from nothing. They say our description stops. They do not say time began. They say time becomes ill-defined. They do not say physics breaks down. They say a particular theory reaches its limits. These distinctions may seem subtle, but they are essential for understanding what modern cosmology actually claims. At the frontier of physics, precision is more important than drama. And what precision tells us is this: the Big Bang is real. The expansion is real. The early hot universe is real. But the idea of a singular beginning is not required, and may not even be meaningful. If modern physics suggests that the Big Bang is not the beginning of everything, then the implications go far beyond cosmology. They reach into the very concepts we use to understand reality. Causality, existence itself. These ideas feel so basic that questioning them seems almost absurd. And yet, when we examine them through the lens of modern physics, they begin to look far less fundamental than we assume. Let us start with time. In everyday experience, time feels absolute. A steady flow that moves from past to future, independent of anything else. We organize our lives around this assumption. We remember the past, experience the present, and anticipate the future. But physics does not treat time this way. In relativity, time is not a universal backdrop. It is part of spacetime. intertwined with space and influenced by motion and gravity. Different observers experience time differently. There is no single cosmic clock. This alone complicates the idea of a universal beginning. But quantum gravity takes the challenge much further. In many approaches to quantum gravity, time does not appear as a fundamental variable at all. The most basic equations describe relationships between states without referring to time in the usual sense. Time emerges only in certain approximations, when systems behave in ways that allow us to define change relative to something else. This is not a minor technical detail. If time is emergent, then it does not exist at the deepest level of reality. It exists only when conditions allow it to emerge. And if time does not exist fundamentally, then asking when the universe began may be like asking what temperature existed before heat. The question assumes the existence of the very thing whose origin is under discussion. This creates a profound shift in perspective. Instead of thinking of the universe as something that began at a moment in time, we are invited to think of time as something that arose within the universe. This reverses the usual picture. Time is no longer the container in which the universe exists. The universe is the context in which time emerges. Once the shift is made, the idea of a first moment loses its necessity. There may be no earliest instant. There may be no temporal boundary, only a regime beyond which time itself is not defined. This has direct consequences for causality. Causality, as we understand it, depends on time. Causes precede effects. Events unfold in sequence. One thing leads to another. But if time is not fundamental, then causality may not be either. This does not mean the universe is random or lawless. It means that the deep structure of explanation may not be causal in the everyday sense. At the most fundamental level, reality may be described by correlations rather than causes. Certain states may be related to others without one producing the other in time. This idea already appears in quantum mechanics. Entangled particles exhibit correlations that cannot be explained by signals traveling through space and time. The relationship exists, but it is not mediated by a cause in the classical sense. Quantum gravity may extend this lesson to spacetime itself. At the deepest level, the universe may not evolve from past to future. Instead, it may exist as a network of relationships that only appears temporal when viewed from within certain regimes. If this is correct, then the idea of an origin becomes even more problematic. Origins assume causes. Causes assume time. Remove time, and the concept of an origin dissolves. This does not mean that the universe has no explanation. It means the explanation may not take the form of a story that begins. Physics has always warned us about this possibility. The deeper we go, the less reality resembles human intuition. Atoms do not behave like miniature billiard balls. Particles do not follow definite trajectories. Space and time may not be continuous. The expectation that the universe must have begun is another intuition that may fail at fundamental scales. From this perspective, the Big Bang is not the first cause. It is the earliest stage of cosmic history that can be described using time and causality. Beyond it, the language of before and after may simply not apply. This reframing has a surprising consequence. It removes the need for a cause of the universe in the traditional sense. Not because the universe appeared without reason, but because the concept of reason itself may need revision. Physics explains phenomena by identifying patterns, symmetries, and constraints. It does not always explain them by tracing chains of causes. The laws of physics are not caused by anything else within physics. They are descriptions of how reality behaves. Similarly, the existence of the universe may not have a cause within time. It may simply be the case that certain structures exist, and from those structures, space-time and time emerge. This idea is unsettling because it offers no narrative closure. There is no moment of creation, no cosmic ignition, no dramatic transition from nothing to something. Instead, there is structure. And from that structure, everything else follows. This does not answer every question. It raises new ones. Why does this structure exist rather than another? Why do the laws take the form they do? Why does time emerge in the way it does? These questions may eventually have answers, or they may mark the limits of explanation. Physics does not promise answers to every conceivable question. It promises internally consistent descriptions of the patterns we observe. The idea that the universe must have a beginning is not a pattern we observe. It is an expectation we project. Recognizing this is one of the most difficult steps in understanding modern cosmology. We want the universe to make sense in the way stories make sense. We want a first chapter, a moment where everything starts. But the universe is not a story. It is a structure. And structures do not always have beginnings. A circle has no starting point. A mathematical relationship does not come into being. It simply exists. The universe may be more like that than we are comfortable admitting. This does not diminish its mystery. It deepens it. The absence of a beginning is not a loss of meaning. It is a shift in where meaning resides. Meaning moves from origins to relationships, from causes to constraints, from beginnings to structure. This is why many physicists are careful not to overstate claims about cosmic origins. They recognize that the deepest questions may require new conceptual frameworks, not just new data. And until those frameworks are fully developed, the most honest answer remains restraint. The Big Bang describes a real and well-tested phase of cosmic history. It does not describe the birth of everything. Time, causality, and existence themselves may be emergent features, not fundamental givens. If that is true, then the universe does not need a beginning in time. It needs only to be. At this point in the discussion, it is tempting to feel that we have reached an impasse. If the Big Bang is not the beginning, if time may be emergent, if causality itself may not apply at the deepest level, then what exactly can science say with confidence? This is where clarity becomes essential. Science does not aim to explain everything in the same way. It aims to explain what can be tested, constrained, and coherently described within a given framework. Understanding what science can say, and what it cannot, is not a limitation of knowledge. It is a definition of intellectual honesty. Let us begin with what science can say. We know, with extraordinary confidence, that the universe has expanded from a much hotter, denser state. This conclusion does not rest on a single line of evidence, but on multiple, independent observations that converge on the same picture. The cosmic microwave background shows us the universe when it was approximately 380,000 years old. Its temperature fluctuations encode information about the geometry, composition, and evolution of spacetime with remarkable precision. The abundance of light elements such as hydrogen, helium, and lithium matches predictions of nuclear processes that occurred in the early universe. The large-scale structure of galaxies follows patterns that can only arise from tiny primordial fluctuations amplified by cosmic expansion. These observations do not merely support the Big Bang model. They require it. The early hot universe is not a hypothesis in doubt. It is a measured reality. But what science cannot say, at least not yet, is whether this hot, dense phase represents the absolute beginning of existence. This distinction is subtle but critical. The Big Bang model describes how the universe evolved once it entered a regime where our physical theories apply. It does not describe how or why that regime came into being. This is not a gap that can be filled by better telescopes or more precise measurements alone. It is a conceptual gap. Physics relies on models. Models rely on assumptions. And every model has a domain of validity. When a model is pushed beyond that domain, it does not slowly become inaccurate. It breaks. This is exactly what happens when classical cosmology is extrapolated to arbitrarily early times. The mathematics ceases to produce physically meaningful results. Not because nature becomes undefined, but because the model does. Science can tell us where its descriptions stop working. It cannot tell us what lies beyond without new principles. This is where many misunderstandings arise. Popular discussions often treat unanswered questions as failures of science. But unanswered questions are not failures. They are the boundary markers of progress. Every major advance in physics began with a recognition that something could not be explained within existing frameworks. The ultraviolet catastrophe led to quantum mechanics. The perihelion precession of Mercury led to general relativity. The incompatibility of quantum mechanics and gravity is leading us toward quantum gravity. The question of cosmic origins belongs to this pattern. Science does not yet have the tools to describe the universe at the deepest level. That is not because the universe is unknowable. It is because our theories are incomplete. This incompleteness does not justify inserting certainty where none exists. It does not justify claiming that the universe came from nothing, or that time began, or that a singularity is physically real. Those claims go beyond what science can responsibly assert. Instead, science draws a careful line. On one side of the line lies well-tested knowledge. On the other side lies speculation. This line is not permanent. It moves as understanding deepens. But at any given moment, respecting it is essential. What science can also say is that many questions humans instinctively ask may not have answers in the form we expect. Why is there something rather than nothing? Why does the universe exist? What caused the universe to begin? These questions are not meaningless, but they may not be scientific questions in the usual sense. Science explains phenomena by identifying patterns, laws, and relationships. It does not explain existence itself in the way philosophy or theology attempts to. When we ask why the universe exists, we may be asking for a kind of explanation that physics is not designed to provide. This does not diminish science. It clarifies its role. Physics tells us how the universe behaves, not why it exists in the deepest metaphysical sense. Confusing these domains leads to frustration. It also leads to false expectations. We expect science to provide ultimate answers, when its true strength lies in providing reliable, testable descriptions of the world. Understanding this helps resolve a common tension. Some people interpret scientific caution about cosmic origins as evasiveness. Others interpret speculative answers as overreach. Both interpretations miss the point. Science is not withholding answers. It is refusing to pretend. There is another important aspect of what science can say. It can constrain possibilities. Even without knowing what lies beyond the Big Bang, physics can rule out many ideas. Any theory that replaces the Big Bang must reproduce the successes of standard cosmology. It must account for the cosmic microwave background, nucleosynthesis, large-scale structure, and the observed expansion history. It must be consistent with quantum mechanics and relativity in regimes where those theories have been tested. It must avoid producing new infinities or contradictions. These constraints are powerful. They dramatically narrow the space of viable theories. This is why progress in fundamental physics is slow. Theories must satisfy many conditions simultaneously. Most ideas fail. But the few that survive are shaped by reality itself. This process is often invisible to the public. What is seen instead are dramatic claims about multiverses, timeless realities, or universes without beginnings. These ideas are not inherently unscientific, but their status is often misunderstood. They are not established facts. They are exploratory frameworks. They are attempts to push beyond known boundaries while remaining consistent with known physics. Treating them as conclusions rather than proposals distorts their meaning. Science does not advance by declaring victory over mystery. It advances by refining the questions. This brings us back to the central theme. The Big Bang is not wrong. It is incomplete. It tells us about a phase of cosmic history. It does not tell us about the ultimate origin of reality. This incompleteness is not a flaw. It is a feature of honest inquiry. The universe is under no obligation to be fully understandable to us at this stage of our intellectual development. The history of science suggests humility here is warranted. There were times when atoms were invisible, when galaxies were unknown, when the expansion of the universe itself was unimaginable. What seems mysterious now may one day seem obvious. But it will not become obvious by pretending we already know. It will become obvious by respecting uncertainty and pushing carefully against it. This is why the most responsible position on cosmic origins is not certainty, but openness. Openness to new frameworks. Openness to new concepts. Openness to the possibility that our deepest intuitions are wrong. Science can say what the universe has done. It can say how it behaves. It can say where our descriptions fail. What it cannot yet say is whether the universe began in any meaningful sense. And recognizing that boundary is not a defeat. It is a sign that we are asking the right questions. At the end of this journey, we arrive at a quiet conclusion. Not a dramatic revelation. Not a final answer. But a boundary. And that boundary matters more than certainty ever could. For centuries, human beings have searched for beginnings. We look for first causes, first moments, first sparks. We assume that to understand something fully, we must trace it back to where it started. This instinct has served us well in everyday life. But the universe is not everyday life. When we apply this instinct to the cosmos, we run into a problem. The deeper we look, the more the idea of a beginning starts to dissolve. Not because the universe is mysterious by design, but because our concepts are limited. The Big Bang remains one of the greatest scientific achievements in history. It explains the expansion of space, the cooling of matter, the formation of structure, and the cosmic background radiation with extraordinary precision. Nothing in this discussion undermines that. What it does undermine is something else. The assumption that explanation must end in a first moment. The Big Bang does not fail because it does not explain the ultimate origin of the universe. It succeeds because it explains everything it claims to explain. The failure occurs only when we ask it to answer a question it was never designed to answer. And recognizing that difference changes how we see the universe. It replaces the image of a cosmic explosion creating everything from nothing with something far more subtle. A universe that may not have begun. A time that may not be fundamental. A reality whose deepest structure does not fit into human stories. This is not a loss of meaning. It is a shift in where meaning lives. Instead of locating meaning in origins, physics locates it in structure. In relationships. In patterns that hold across unimaginable scales of space and time. The universe does not need a beginning to be intelligible. It needs consistency. And consistency is exactly what modern physics demands. This is why physicists are careful with their language. They do not say time began. They say time becomes ill-defined. They do not say the universe came from nothing. They say our descriptions reach a boundary. These are not evasions. They are acts of precision. At the edge of knowledge, precision matters more than confidence. There is something deeply human about wanting a beginning. It gives closure. It gives a sense of control. It makes existence feel explainable in familiar terms. But the universe does not exist to comfort us. It exists. And our task is not to force it into stories that feel satisfying, but to understand it as honestly as possible. What we have learned is not that the universe has no explanation. What we have learned is that explanation itself may not take the form we expect. Physics has shown us, again and again, that reality is stranger than intuition, but more coherent than imagination. Particles are not little objects. Space is not a fixed stage. Time is not a universal flow. And beginnings may not be real in the way we think they are. This does not make the universe meaningless. It makes it deeper. The absence of a beginning does not imply chaos. It implies structure without edges. A reality that does not start or stop, but simply exists according to principles we are still uncovering. This perspective also restores something important. Humility. Not the humility of ignorance, but the humility of understanding where knowledge ends. Science is at its strongest not when it claims final answers, but when it clearly distinguishes between what is known, what is plausible, and what remains open. Right now, the ultimate origin of the universe remains open. That is not a weakness. It is an invitation. An invitation to develop deeper theories. An invitation to rethink fundamental concepts. An invitation to accept that some questions may outgrow the language that gave rise to them. The universe has not failed to give us answers. We are still learning how to ask the right questions. And that may be the most important realization of all. Because once we stop insisting on a beginning, we stop mistaking boundaries of theory for boundaries of reality. We stop treating our ignorance as cosmic drama. And we begin to see the universe as it actually is. Not a story with a first page, but a structure we are slowly learning to read. If you take one idea away from this exploration, let it be this. The Big Bang is real. The expansion is real. The early universe is real. But the idea of an absolute beginning is not required, and may not even be meaningful. The universe does not owe us an origin story. It owes us only consistency. And consistency is exactly what it delivers. If you found value in taking the time to understand where science truly stands, not simplified headlines, not dramatic shortcuts, but the honest edge of human knowledge, consider subscribing. This channel exists for those who prefer clarity over certainty, depth over spectacle, and understanding over easy answers. New explorations like this take time, care, and patience. Your support helps make them possible. Thank you for staying with me through this long journey. Sleep well tonight, and when you look up at the night sky, remember this. What lies out there is not a universe born from nothing. It is a universe still revealing itself. And the greatest mystery is not where it began, but how much there is left to understand.